Okay, so last time we learned in section 5.1, we learned about a certain point in a triangle that gives us the circumcircle. It's the circle that goes around the triangle and passes through all the vertices. And this time, in 5.2, we're going to find out about a new point. It gives us a point that gives us the end circle. Kind of interesting thing. And so let's take a look and see how that happens. So I'm going to do part 1 of this lesson, and as you go through this lesson, once we get to certain problems, you'll work those out. And if you like, you could try to work them out first by yourself, and then I'll work out some of the problems for you if you get stuck. And so that's really all you need to do. So let's go ahead and go through this. Okay, so angle bisectors. This is something we had way back in chapter 1, I think, where we had angle bisectors and angle addition and things like that. So we're going to review some of those ideas. So our goal today is for students to be able to bisect angles of a triangle. And then we want to eventually get to this question. What can you conclude about the point that is on the bisector of an angle? Well, these are some warm-up problems I'd like you to do. And you should have enough room on your PowerPoint slide to just work out the problems in the margin. So the main thing about a bisector, just like a segment bisector, is that an angle bisector cuts an angle right smack in half. And so it means then that this angle here is congruent to this angle over here. If they're congruent, then their measures must be equal. And so that gives us a working equation. These two must be equal. So that sets up this equation, 3x plus 7.5 must equal this angle over here, or the measure of it, 5x minus 32.5. And so that's what we're going to be doing on number 1. And I don't care to waste the time to show you how to solve that. I believe most of you guys can solve that on your own. So I'll let you do that and finish that one up. How about number 2? This looks like Pythagorean's theorem. X squared plus b squared is equal to c squared type of thing. And part of the problem's been worked out for you. So that shouldn't give you too much trouble. 12 squared is 144. So you're then going to move the 144 over here and then take the square root. Well, one thing about square roots, if you have x squared is equal to, say, 16, and you take the square root, okay, square root here and here. When we write x here, we want to write x is equal to plus or minus. In this case, the square root of 16 is 4, so we say plus or minus 4. So you might wonder, well, why do we say plus or minus? That's a good question. So let's go back to the original equation, and we'll see something here. We originally started off with x squared is equal to 16. Well, see, we don't know what value x is. And it turns out that if x is equal to 4, like one possibility is x equal to 4. Why do we say that? Well, because x squared would be 4 times 4, and 4 times 4 does equal 16. So x equals 4 makes this equation up here a true statement. Bam. But you know what? So does x equal to negative 4. That works also because negative 4 times negative 4 is equal to 16 also, because a negative times negative is a positive. So these are the two solutions. So when we realize that, we generalize. Anytime we have a square root equation or a square equation and we're going to take the square root on both sides of an equal sign, we just realize, hey, we've got to put in a plus or minus. Otherwise, we miss some of the possible answers. So again, we have x squared here, we take square root here, square root here. When we do that, we get x is equal to plus or minus. We want to put in a plus or minus there. So that's my little comment for number 2. How about warm-up problem number 3? The legs of a right triangle. Well, again, this looks like it's a little bit of a review for Pythagorean's theorem, which we just kind of did already in chapter 7. And in this case, the legs of the right triangle are 15. Now this length is 20. And we're trying to find the length of the hypotenuse. And so we would simply say, well, 15 squared plus 20 squared is equal to c squared. And I'll let you finish that up on your own. So do these 3 problems for the warm-up on your sheet right here in the margin, somewhere, and just do like numbers 1, 2, and 3. And then we'll go back to the lesson and go to the next slide. So here we go. An angle bisector. It's a ray that divides an angle into 2 congruent adjacent angles. And by adjacent, we mean that the angles must be next to each other. They have a common boundary, and that common boundary is the angle bisector. We should maybe just draw one real quick, just to make sure we understand. An angle bisector is going to cut something right smack in half. We'll just call this the angle bisector of this blue angle, so that this angle here is congruent to this one. But here's the thing, the angle bisector gives the 2 angles a common boundary, and that common boundary is what makes them adjacent angles, or like neighbors, Well, okay, what to do, let's move on. What else do we have? Note, the distance from a point to a line is the length of the perpendicular segment from the point to a line. Okay, so that's kind of an obvious thing. I mean, if you have a line here, think of this as road, and maybe there's this tree over here, or this pole or something, represent this by a dot. What is the distance from this dot to the road? Well, which path would you take? Would you take this path over here? See, that's the distance? Well, no. We'd take the shortest path, right? And if we took the shortest path, we'd go like this. And when it hits this road here, it'd make a right angle, like that. Well, that's how we're defining distance from a point to a line. It's always the shortest path, and it's always going to make a perpendicular segment when it hits the road or the line over here. And of course, perpendicular means that we're going to have a 90-degree angle here. So that's what we'd have, something like that. Okay, well, I hope that makes sense. So let's keep moving. Here's a new theorem then. The angle bisector theorem. If a point is on the bisector, that's somewhere on this bisector, then it is equidistant from the 2 sides of a triangle. So let's kind of draw this out in slow motion now. Remember, we start off with an angle like this. Okay, there's our angle. We then bring an angle bisector into the picture. Okay, like this. Alright. And now what we do is we pick a point somewhere on that bisector. Pick any point you want. Now, the distance to this ray here, remember, it has to make a right angle, right? So it makes a right angle right there, bam. And it's the shortest path. And likewise, the same point can go to this side over here. And it's got to make the shortest path, right? So it makes a short path right there, and it makes a right angle there. Okay, so what are we going to say now? What we'd like to say is that these 2 sides here are congruent, right? Okay, well, why can't we say that? Well, I'd like to show you how. It shouldn't take too long. Well, what we know is, since this is an angle bisector, we could say right off the bat that, let's use this color. we could say that this angle is congruent to this one, because that's the definition of an angle bisector. Okay. We could also say that this side is congruent to itself. So we have an angle, okay, we have a side, and we have an angle. That's a right angle. So we have angle, angle, side, and we have angle, angle, side. And we learned way back in chapter 4 that two triangles are congruent by several theorems. We can use side, 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 remember? We can use side, angle, side. We can use angle, side, angle. We can use angle, angle, side. And we can use hypotenuse, leg. Well, this is the one we just now used. And so in this case, these two triangles are congruent. Well, then we could use the idea CPCTC. Corresponding parts of congruent triangles are congruent. And since these two are the corresponding parts, we now can say that that side is congruent to that side. So there you have it. There's our theorem, and I just proved it for you. And you should be glad we're not going to do any proofs in this assignment. At least I don't think we are. So let's continue. Here's another idea, is converse. So let's take a look and see what this one says. If a point is in the interior of the angle and it's equidistant from the sides of the angle, then it lies on the bisector of the angle. So let's take a look and see how this works again. Let's start out again. We have an angle like this. We start off with an angle. Okay. The next thing we have is a certain point somewhere on the interior. It can be anywhere on here. But let's just say it's right here. And we measure this distance to this side over here. Remember, it's got to make a right angle. And we measure the distance here. Now let's say you come along and say, hey, you know what? That's 5 inches. And hey, you know what? This is 5 inches. Well, the only way that happens is if this line here is the angle bisector. You see? And so how would we know that it's going to be the angle bisector? Well, first of all, we are allowed to do this. We are allowed to draw a line from this vertex to that point there. We can draw that in. We're allowed to do that. That's called an auxiliary line. So we'll just draw that line in. And by doing so, it creates two triangles, one up here, one right there. We already know that this side is congruent to this side. And we already know that this is a right angle right here. And we know that's a right angle. And so we also know that this line right here is congruent to itself. So since we have a right angle, we can use the theorem called hypotenuse leg. And that hypotenuse leg, this is the hypotenuse. See, remember that's the opposite side of the right angle. So that this side here is the hypotenuse. And this side here is the hypotenuse. And this here is a leg. There's a leg there and there's a leg there. So by the hypotenuse leg, these two triangles are congruent. And so after we say that those two triangles are congruent, then you can say that this angle is congruent to this angle by CPCTC. So yeah, it took me a moment to remember that idea. So anyhow, so I've proven for you both of these theorems, so we know they're true now. So let's go ahead and move on. We're going to try some problems now. And let's look at example 1. Find the measure of BAD. Well, first of all, since these two distances are the same, it means that this here is an angle bisector. And it bisected this angle right here. And so it means it cut it right smack in half. And so it also means that these two are equal. So angle BAD, well, that's easy. Angle BAD is equal to 54 degrees also. Man, is that simple. Okay, well, let's move on. Example number 2. Well, what value of x does P lie on the bisector? Well, if this is a bisector, then that would mean that these two distances are congruent based on the first theorem that we talked about. And if those are congruent, then we know that these two sides are congruent, or the length of their sides are congruent, or equal. And so we get an equation, 3x minus 6. This should remind you of the types of problems we had on the warm-up. We're doing things like this. So, anyhow, if we get some x's together, I'm going to subtract x here, subtract x here. I get, what, 2x over here is equal to, let's move this 6 over to the other side. We're going to add 6. I get 2x is equal to 14. And then divide by 2, I get x is equal to 7. Now only a bozo stops there. We don't stop there. We try to answer what we're being asked. It says, for what value of x? Oh, well, we did find that. We found the value of x right here. X is equal to 7. So there you have it. We have example 2. Now this is where I'll stop for tonight's lesson. And we will do the second part of this lesson tomorrow in class. And we'll try to wrap up section 5.2. Okay, bye now.